future of computer-aided design and manufacture. Before I start to show the images that I prepared today, I kind of wanted to give a context of what my background is and how I came to, how I came to be interested in this particular theme within architecture and design, and what my approach has been over the last few years. And Sarki's read a little bit of my background. So just an anecdotal experience that I want to relate. When I started studying architecture, I don't know, 15 years ago, I actually was trained in a very traditional manner, where I started, with the pens, drawing on Mylar, and within just a few years of doing a bachelor's degree and then going for my master's degree, I was, using form-finding technologies like Maya and using the first ever 3D printers in institutions that were becoming a little more prevalent at that time. So it was this really stark contrast for me as a person who was kind of undergoing this academic experience and a schism. And then to expand on that, I guess to have it even exacerbate, when I went to practice right after that, it was at the time when practices, especially in Los Angeles, like Morphosis, like Frank Gehry, and a lot of other smaller practices like Graft, which was a very small practice, were starting to take this really new technology that was coming from outside of our profession, outside of architecture, outside of design, and trying to discipline it the way we are taught as architects to discipline things that come from outside of our profession. So anyway, that's just a little bit about my experience coming to terms with this kind of technology. Now, what I'll talk about today, what I'll show you today, is probably focusing on the last few years of what's going on both in the academic realm, but also in the professional realm. But I wanted to draw that arc because I think the two work together really well in order to exploit the kind of benefits of new technologies that come about in our industry. In academia, it's what that realm is what sort of proves concept. It's a proof of concept work that happens, and oftentimes it's very focused and sort of removed from building scale, but it really does trickle up, and then vice versa in practice, taking kind of the academic experiments that happen within the institutions around the world and trying to actually make them applicable to building conditions and building codes and so forth. So basically, I think I'm going to talk about things in terms of those two extremes, those two views. Okay, so I started with this slide because essentially these were the tools that came about, or that sort of started becoming ubiquitous at the time when I started studying architecture, and are still quite, some of them are a little bit more than others, but basically these were the tools that enabled us to kind of go into territories we were never able to go into before, and explore geometries and kind of strategies that we were not able to get a handle on and control as we were before. And a lot of these, Maya being one of the first ones, came from outside of our profession, the animation arena, and then Rhino and Grasshopper, even Digital Project, which was adapted from Dassault Systems aerospace industry programs, sort of followed suit because they saw the niche, they saw the need there for it. Just some interfaces of those programs, as you all know probably. I'm preaching to the choir here. So, and then of course the kinds of what we used to term as the emergent technologies, which I don't call anymore the emergent technologies because they've really they are here. They've emerged. We've been kind of working with 3D printers, laser cutters, and a spectrum of other technologies in between those two that for the past 10, 15 years. So, but these technologies that came from outside of the profession were really enabled by those design programs that I showed in the first slide. And so the two kind of technologies and techniques combined together are what spawned the imagery and the research that I'm going to talk about in the next few slides. So just a quick recap, the 3D printing on the right, the kind of series of shelf-top 3D printers that are now coming out that are becoming very, very accessible to everyday kind of working situations, versus the industrial 3D printers, which were used for many years for super high-tech industries such as the medical industry or the car manufacturing industry and parts that had to be extremely precision made. But now these kinds of technologies are being utilized for a variety of other design disciplines, as you see here, to inventing new musical instruments possibly, to the entertainment industry, to prosthetics. There are actually quite a few dentists in Los Angeles that are printing teeth, to prosthesis for animals and human beings alike. This was a duck that was fitted with a prosthetic leg, to 3D printing food, which is something the aerospace engineering industries are looking into. This is a Mobius strip bacon, because it's a lot more efficient and kind of tends to produce much more customization, to have the machinery and the parts, and then kind of specify the output as opposed to packaged food and taking that up to space. So
we can get fat-free bacon, right?
What?
We can get fat-free bacon.
You can get fat-free bacon. It's mass customization. You can get yes, of course. But that wouldn't be bacon. It wouldn't be very good. And then, so now I just want to move in a little bit into the more focused design industry and how we've used this kind of technology more traditionally, let's say 10 years ago, which it was used purely for representational purposes. So you were printing rather small scale models, sometimes with varying degrees of accuracy depending on how much time or material you had access to. So models like this, for instance, variations. This is a student project. This is kind of a smaller representation of a desk and a shelf unit, to large building models that were represented in this scale, and even to Frank's models, who was somebody who never used 3D printing, but is now starting to acclimate that kind of technology into his practice. The glass. The kind of transparencies on these buildings are 3D printed. And this goes without saying, it's not just the 3D printer, but the generative design aspect of these technologies that fit together. This is Aranda and Lash's studies. So this kind of evolution of not just mass production, but mass customization. So you didn't have to you didn't have to be weary of how much material you were expending. You could really do a number of one-offs. You could think about producing a number of one-offs. It was not just about focusing in, honing in on one rigor, one mold that was going to produce the same form over and over again. Also a covered unit by Aranda and Lash that's using the same 3D printed technology, and now jumping scale. This is actually a wall that's 3D printed. So the size of these kinds of printers growing, and then the material use expanding from powder to polyresins, from opaque to transparencies, and then to metal printing, which is a fairly new phenomenon, very expensive, but it's going to be more and more more and more commonly used. This is a piece by Rui Klein. It's an exhibition piece, but it's cast. It's not cast. It's actually printed with metal polymer. It's the same piece. That the bottom is a study piece, earlier piece, but the three images are the same piece, just showing various lighting affects. So I guess along with this technology evolution, one thing that I think I'll just talk about, and maybe I take it for granted because this is the kind of practice, these are the practices I've been a part of, but so the exploration into producing new affects and sensations with form has been really key in the last 10 to 12 years. So it's not just about form finding, but it's about how does that sort of further inform the environment we live in? How does that further inform the experience that people have in terms of interiors, materials, and then extended to building scale, which has been a little bit, that leap to building scale has been a little bit more difficult, but I think we're getting there. For instance, this is the prototype for the first 3D printed room. This is the couple of in-process images. They're uncovering it from the powder there, and then this is actually the one piece of that 3D printed room, and I'll show a little clip in just a moment of that. Then a few years ago, Andrea Morgante did this very kind of 3-meter high pavilion, which she used the first ever, so the largest 3D printer constructed to actually print this life size, which was, these were the results. And then now we're getting to a point where there's 3 firms who are competing for the first ever printed house. This is one plan. This is actually a combination. Some of the formwork will be printed, and then it will be it will be cast with a material. So
But there's assembly involved here?
there is assembly involved here, and then we're moving away from that. There's still assembly involved in the second one. This is the second proposal for a 3D printed. It's a house on the canal in Amsterdam. This is the large 3D printer, and then they're printing components of that house, such as the window. So this is actually the window for the house, but it still requires quite a bit of assembly. To a very kind of extreme, or let's say refined version, in terms of assembly and in terms of joinery or using any other kind of attachments, was this proposal, which is the kind of the nest house. And they don't imagine any external joinery, any external kind of mechanisms in terms of attachments. They have been very reliant on the nest network structure to make it this kind of holistic entity, and expect it to be printed perhaps in parts, but then come together more like a Velcro system they talk about. So then laser printing, just quickly, I've categorized things in terms of technologies, but of course there's cross-breeding between these technologies. Some of the study models at Frank Gehry's office, which again, someone who traditionally makes models by hand and has been hanging on to this practice for many years, has started incorporating the use of laser cutters and 3D printers. Not all of these models, but this first one in particular is laser cut basswood that's stacked for a project in Arles, which was modeled and then kind of filed to factory output to that particular model. And this is a segment of it, so I just sort of wanted to show the scale calibration, right? So the laser cutting is happening on a representative scale, where the model has these layers of basswood that are it's just meant as a representation, but it's also happening on a mock-up scale. So the 2 images on top are a mock-up, a 1-to-1 mock-up of the same project, but also CNC laser cutting was used to cut the various strata of this aluminum aerated panel. So going from that, okay, to this. So the scale calibration is starting to happen. And then just some kind of simple, straightforward projects that are laser cut. And I'm sure you guys already know about this, but this whole idea of being able to kind of calibrate between a flat, expansive surface and a 3D surface, and the techniques that that entails. Again, with the software that we've kind of adopted, the 5 different softwares that I showed. So these are just some projects utilizing laser cutting. This is a student project that was done as a studio project at SciArc. These are actually my student projects. Undergrad students that did this work with a laser cutter. Again, same. And to someone like, for instance, Elena Manfredini, who's an architect who initially started studying the implications laser cutting could have on fabric, but then that evolved, that kind of proof of practice, or that kind of working with a very frivolous, let's say, material, right? Fabric, fashion. I mean, I'm using architectural terms to describe it as frivolous. To this exhibition that she did, to furniture, to the Chinese pavilion that she did last year. So I mean, I think the value of learning in terms of doing the projects that she did with fabric, with a kind of lace-like structure that she did, the furniture, and then being able to sort of take that learning curve and apply it to an actual structure in terms of all that entails: joinery, detailing, drawings, the fabrication process. Similarly, the very many an architect from France who's doing these pavilions that sort of use, let's say, one or two components, like a donut-shaped component or a cylindrical-shaped component, and they can be taken apart and put back together, but focuses on the kind of fabrication technique and language that is shown here. For instance, in that image, it's printed as flat panels. You know, the bulk of the work is done ahead of time, right, in the computer, the kind of curating not only the design, but also how it's going to come together and how it's going to come apart. So this transition from kind of the traditional method of putting things together and breaking them apart to calibrating that as part of the design process. Another architect actually here who did this experimental installation at SciArc with Mylar. So if you've ever dealt with Mylar, it's very flimsy, but through certain techniques of cutting and reinforcing, she was able to make these sort of soft walls. This hanging pieces that Ball and Noakes does in Los Angeles. Anyway, these are all similar. And to this idea of kind of the modular system, modulated system, which a lot of architects are now starting to attack because it's an attractive idea. The modular system in the past has been one repetitive unit that keeps, it's one unit that keeps repeating, but now we have the opportunity to have a unit that doesn't necessarily have to repeat. It could be various units that fit together or various configurations. So this kind of idea combined with the robotics, which I'll show in later slides, is something that's very interesting for various academic studies. This is a student project, just tackling the idea of the brick. So you know, these are laser cut strips, but the concept is that they're bricks. And how do you stack them together? How do they go together in the immediacy of one unit, and then how do they interact with other units next to them? Then similarly, another installation by Iwamoto Scott that tackled, not as bricks, but tackled as panels, leaf panels, the pavilion that was up at SciArc a few years ago. Okay, so, and then on to some CNC technologies, which I'm gradually building up to the robot technologies, but I want to give a bit of background as to why they're being dealt with in the way that they're being dealt with today. So CNC technologies, of course, coming from other avenues. We use them very traditionally for topo models or various complicated models. There are architects that use them in combination with traditional techniques. For instance, again, Aranda and Lash, who use CNC milling for these very complicated parts, but then like highly skilled manual labor to put the parts together. So there's this experimentation between high technology, or combining high technology and low technology, which I think is a very valuable and underexplored area. This is another system that they did, and then a smaller scale project, which was a table. Similarly, this was a 3D milled project by the Very Many. And then to go from strict milling to milling molds, right? This was a project that Greg Lynn had done many years ago, where you milled a mold, but then you actually spent quite a lot of manual labor putting the fiberglass on there. And this lantern is made of fiberglass. That's what they're kind of sculpting onto the mold. It's actually a very manually laborious process, and it's very toxic. And now they're coming up with better adhesives, but still, it's just interesting that that combination of high and low technology could go together. That was the method Zaha Hadid used for her Chanel pavilion here. I mean, it's all glossy and looks very nice on the outside, but it was a very laborious process. And then, again, in this like spirit of utilizing half high-tech, half low-tech, this was a project that didn't get realized at Frank Gehry's office, but it was a winery with a freeform trellis that we worked on, then materialized the trellis, and tested various cementitious materials on how to make this. How do you make this kind of freeform trellis? So we ended up building lots and lots of molds, exerting lots of energy on molds and rigging how these various layers can go together. So yes, very high-tech process of building molds, very accurate, but then extremely laborious artisanal process of actually building the layers of this trellis into those molds. Then vacuum forming, which is has been kind of a staple at school, actually. There are quite a few people, colleagues of mine at Los Angeles, there are specifically 2 who do a lot of research in vacuum forming. They do a lot of research in vacuum forming because, yes, we use vacuum forming at school, but this kind of extrusion, aluminum extrusion, happens it's kind of a very straightforward bridge to building facade systems. So while these are plastic studies, we can easily imagine that with a kind of technology upgrade that we have access to, these can be aluminum panels or other kinds of panels. So these are some student projects of aluminum, plastic vacuum formed systems.
Do you call it vacuum formed?
It's vacuum formed because because of this mechanism here. So there's a vacuum pump that sits at the bottom here, and then the mold that's usually CNC'd goes there. Then the plastic is kind of draped on top. I mean, you can see it better. You can see it in process here. And then this heater essentially comes down with great force and molds that plastic with heat to the actual mold underneath it. But the vacuum and the heat, the combination of those two, sort of make that mold happen. And these were all made in the same way. I mean, they're panel systems essentially, but they were all made in the same way. This was actually one of my students last semester. It was an Armenian girl who's amazing. And then Florencia Pita, who does a lot of research with this kind of applique, like blurring the boundary between visual art, architecture. Again, this is based on the concept of Legos. Legos snap together, so she's actually kind of fabricating the underside and then the over snapping mechanism, and so these two things snap together. So there's a lot of experimentation in trying to create new materials or new technologies with what is coming from outside the discipline. This was similarly kind of a floor-to-wall system, and then a project by Servo that was integrating sensors and lighting. So the kind of receiving covers of these were 3D printed, or were vacuum formed, and then sensors were integrated such that you could meander through this scape, and the sensors would go on and off as they felt heat or a person coming closer, moving further away. And then this is a larger student project at Washington University that experimented with this vacuum forming system, but as an interior cladding system. So they started with this idea of the kind of articulations, the muqarnas in mosques, and then expanded on those patterns, eventually came up with a panel system of their own, and then a fabrication logic. So they had to undertake a few steps. They laser cut some of these plastic panels into patterns, much the way you do with clothing before you start sewing. And then those laser cut panels were then vacuum formed to specific molds. So they had laser cutting, they had CNC milling for the molds, and then they were vacuum forming to those molds. And you see them here with the panels that they color code and spray paint at the end, which starts to look something like this, and then the final assembly starts to look like that. And then backlighting, this is the final piece installed. So this technology also used by lots of practitioners. For instance, Zaha Hadid in many installations. This is the master plan for Istanbul that she did, for a portion of Istanbul that was then exhibited as its own sort of entity at a New York gallery. The interior of this gallery, all of the lighting fixtures were then vacuum formed. We vacuum formed models for a competition at Gary's office. And so here I'm going to jump to a couple of slides that don't have to do with vacuum forming, but I wanted to illustrate the idea of scale, the idea of doing research on a small scale and then applying it to the large scale, which is something that I think the fish, Frank Gehry does the fish, but the laser cut kind of panels and the arrangement and the modeling of these small fish directly contribute to the glass cladding of the large fish. Then if I jump to architecture, a firm like Herzog and Demeron, which is starting to experiment, I mean, they've been experimenting with materials for many years, but more recently with their Hamburg project with the slumped glass, which is same technique, different material calibration. I mean, we're jumping exponentially, but it's essentially the same technique in slumping glass to articulate the kind of half circle indentations they have here, which you'll see from the inside here, this particular piece that they're installing, and then you read it as this kind of gradient as you approach the building, which is that piece there. So another new technology that lots of kind of younger firms have been experimenting with recently, Peter Testa did this carbon fiber tower that was like a pie in the sky idea many years ago, but recently there have been a lot of firms that have been actually experimenting with cast fiber or sandwiched fiber, and that technology comes from the sailing industry, the nautical industry, which uses this means to customize their sails. These are like really high-tech racing boats, and they have very specific molds, and then they can use of CNC and kind of computer-aided design, they can lay down fibers densely and less densely exactly where they need to reinforce structurally or to kind of reinforce nautically what they need the sail, how they need the sail to perform. So here is a guy in the factory kind of driving the machine, laying down the fibers. Then they lay down a layer of kind of adhesive. So this is essentially the layering process, and that is the final sail. This is a close-up of the fibers coming to a point. So this is the kind of technology that now, yes, there have been practitioners that have actually been using the sail companies to experiment with this, but then also the kind of robot fabrication technology I'm going to show you now is able to do a much smaller scale experiments with this kind of fiber technology, which I think was pioneered by Peter many years ago. So these are kind of experiments in densification. How can you densify a certain node to render a certain kind of structural behavior from it? Then recently, well, not recently, a few years ago, Greg Lynn used it as a means of creating this furniture piece, and you can actually gain quite a bit of transparency from it, by laying down fiber strategically and then having the glazing, the resin glazed over it. Then University of Stuttgart did this pavilion as an experimental piece where they interwove opaque and transparent fibers in an effort to sort of study the difference between their interaction with the sun. This is a close-up view of it. And then the interweaving of those fibers actually. And they use robot fabrication, which is what I'm going to move into now, essentially, which I think sort of ties all of what I've talked about together, because robots having 6-axis capacity and the end-of-arm tool customization capacity can really do everything that I've discussed so far, everything I've shown so far in terms of technology, in terms of fabrication. And just as a credit to Peter Testa, I wanted to show his carbon fiber tower, which he did many years ago. So before this, the casting and molding series actually corresponds to the robots as well. This was a blob wall that Greg Lynn did a few years ago, and it was not so successful in terms of the brick idea he wanted to test. But what was successful about it was one of the first uses of these robot arms to calibrate cutting angles. So basically what the wall was, it was a basic unit as a brick, a strange brick, but nonetheless a brick. So it was a basic unit, and what sort of commanded its position in the wall, its position and its leaning in the wall was how the computer dictated the robot to cut the brick. So depending on what node was cut off, at what angle, the bricks could fit together in a very specific way, a predetermined way that was modeled. So this is Greg with the installation at SciArc, and they cut the whole thing and he signed the, anyway. So I think it was successful in the sense that it tested the kind of the robot integration, not successful as a brick system experiment. I don't know why I put this in here. I put this in here because more and more the tendency to work with metal, and this was one of the earliest kind of cast metal pieces. It was actually a tea set that he designed. This Herzog and de Meuron, who's always, I think, really successful at adapting high technology to building scale, which is one of the issues. I think we're building up to building scale, but there aren't a whole lot of people that actually adapt the technology to building scale yet. So these were cast metal features that are on their New York building as a pedestrian walkway. Okay, so robot fabrication. So essentially, the robots, what's the basic unit? Let me show you this too. So the robots can be as large as this. They can be a little bit smaller than this. They're mounted either on the floor, wall, or the ceiling. They have kind of 6-axis moving capacity. They can work on an assembly line, or they can work on their own. They can work together. They can work with human interaction. So lots of flexibility. And currently, the kind of line of study, mainly in academia, with these robots, is basically to see, not just to design new objects, but to also design new processes. So I think what the big idea right now is that we can design end-of-arm robot tools. We can design that. We can actually program them to work together in a very specific way. So the entire process is up for grabs. The entire process is up for grabs in terms of authorship. And I think that that's the key in terms of this line of exploration. So you have folks that are experimenting with robots drawing. You have folks that are experimenting with their own DIY robots, like very, very basic versions that do very specific function, that function very specifically for this one, which does graffiti. And then you have folks who are working with the end-of-arm tool, so designing very specific tools that then manipulate materials in a specific way for a desired result, or sometimes just as an experiment to see where that goes. And I think this is best articulated, this part, by a few clips I have, because I can't really do the robots justice by talking about them. But anyway, this is a project where, for instance, there's 3 robots working in conjunction. One of them is holding the mannequin, spinning it around, while the others are dripping a fiber onto it in a very, not haphazard way, but in a specifically curated way that is being fed via scripting to the robot community that is working together. So in this case, for instance, a top or a garment, but in this case, which uses similar curatorial direction, let's say some kind of a material. And before I show you the clips, I want to show a few works by Gramazzo and Kohler at the ETH, who are doing really solid work in terms of translating this technology to building scale. So with their students, so this was like a 4-week workshop where the students were actually asked to experiment with concrete panels that were going to line the Rhine in Basel. So you can see that they designed their own specific end-of-arm robot, end-of-arm tools. which they worked with cementitious material to either deposit or displace or whatever the techniques that they were working with in terms of formal aesthetics. And then these were some of the results of those panels, which I think are really have potential, great potential. Then they also work with students, but in their own practice, with the notion of the brick wall and how they can work with robot fabrication to vary this kind of what a brick wall means, but how you construct it, et cetera, et cetera. So these were some tests. This is the robot on an assembly line, uses its suction cup, grip, and then is curated by script to place the bricks in a very specific way. I mean, you can also imagine that in the future you can apply mortar to this equation and it becomes, with structural testing, of course, or with structural calibration, becomes a viable solution for buildings. So these are some of the results. That applied to a longer span wall, which they actually did outside. And these are some of those results. And then modifying the brick shape into units that were used to design this particular pavilion, to the most radical idea that they have thus far. This is kind of a scaled version of a 600-meter tower that they propose to be built by robots in a very remote village. And they actually designed those robots, and we'll take a look at a clip that they have for that. And then I think, to the kind of contour crafting robots that people are starting to discuss and talk about in terms of contour crafting, lunar contour crafting, like exporting robots to the moon that can work with the scape that's already there to craft what's necessary, which is quite a revolutionary idea, more about this kind of subtractive involvement rather than an additive involvement. Okay, let me see if I can show you some of those clips. So this is just an example of kind of a drawing course. I don't know. Maybe you need the music. I don't know.
We do.
I do.
You do need the music? Okay.
Yeah.
Didn't feel like 2 minutes, but okay, you get that. And then, yeah, this is this is the displaced basket weave. I mean, this kind of trajectory is more about really designing the process. It's not about the result. It's about what can we do with these machines to exert authorship. It's not playing the middle part, it just plays the beginning and the end. Well, so that was the kind of resin basket weave image that I showed earlier. To this thesis project, for instance, which developed he developed a mechanism to print material in a suspension chamber, in a gelatinous suspension chamber, so you don't need any kind of scaffolding for it. I would really like you to see this, which is that pavilion that they did in Stuttgart. essentially the turntable is turning and then the robot weaves. And it's weaving thread, it's weaving fiber, but there's also a resin head, a resin trail that's coming out of there.
How much programming is behind this? Is it, or
There's-
is a form and that's it?
There's actually this, I wish it would play all the way, because at some point they transition to the digital realm and you can see the model. I mean, it depends on what you're trying to do, but there's actually very simple scripting processes that can happen to mediate between Rhino or Maya and some of the software these robots use to realize it. I mean, with 3D printers, for instance, now there's a lot of open source software. You don't even have to use any of this kind of advanced scripted. Everything's been very simplified, and I think that we're going that direction with this kind of fabrication as well.
So those were the cameras that follow the. Those were the cameras that up there.
Yeah. It has coordinates of where it's going to move, and that's based off of the 3D model. So there's a longer video of this, but I guess this. You don't have to watch the rest. This is just them getting very excited about it. Okay.
They can also disassemble, right?
I guess if they're programmed to. Yeah.
Take it apart.
All right.
But aren't these bricks attached to each other with some glue kind of?
Yeah.
something?
Yeah, this
It doesn't
system
include
doesn't
any
explore
complicated-
mortar yet, but
Mm.
you can imagine that that could be a component. For instance, like maybe you pre-apply it, or I didn't show you the lunar carvings that they have in mind. Those actually show really clearly that you can apply mortar and disassociate or
What is the cost is construction growth? What is the rate of growth of the wall? Is it much
I don't know.
faster than human?
That's hard to say because it may be slower. I'm not sure because that's not something that they share. I mean, at least not something that I've asked or read about. But if it were a simple wall, yeah, no, definitely not faster than human labor. But the point is that they can calibrate very precisely not so simple wall. Whereas for a human being to calibrate that there's human error involved, first of all, and then that slows us down in terms of time efficiency. So that's the kind of trade-off in their studies.
And I have a question. If I have a good 3D model already, and I want to print it, what do I need? What should be the next step to decide what kind of robot I need? What kind of?
If you just want to print it, 3D printer is what you need. You can get the desktop 3D printers and very easily export your file from Rhino, and I mean really easily. You can just go through either the software that comes with the printer or an open source software, and that's all it requires. I mean, you have to have a model that's printable. That's a completely different idea. Like in terms of, there has to be a solid, and there's rules you have to follow in terms of modeling, but in terms of logistics, really that's all you would need.
Is there a variety of 3D printers?
Yes,
So I
large
can choose what I
variety.
need?
There's a large variety of 3D printers, and I guess the crude way to say it is if I go back to, for instance, a few years ago to the articles that came out about these desktop 3D printers that are now becoming more and more kind of available to everybody. Prices are coming down, and so they're becoming more available. Those are purely representational printers, as I was talking about before. You can print something and it sort of captures what it is you've modeled. They typically have settings like low, medium, high, and that depends on how fast you want it to go, how accurate you want it to be. You have to have it's a trade-off. You want it to be very accurate, it's going to be slower. You want it to be somewhat accurate, you can go faster. But those are mainly for representation. What that means is that the precision level isn't at the point where you could print something that you could use as, let's say,
Final product.
not as a final product, because you could possibly use it for an installation, you could use it for building joinery possibly, but not for, let's say, very sort of precise environment, like, let's say, the medical industry, or
Like a gun.
or maybe you can use it for a gun. I don't know.
Isn't that exactly
I don't know
where
what kind of
the-
tolerances
Or jewelry,
that
you know, it's like-
requires. I don't
There's
know.
like a big set of
Yeah.
news stories on this, right, recently?
Yeah.
Not so recently.
And I don't know what kind of these
Now,
things, but
it might be
I just
helpful.
wanted to illustrate the difference. There's still that sort of very high level 3D printing that happens for certain industries. It's yet to become kind of available to us as a desktop mechanism. There's still kind of a quality difference. So one is representational quality, the other one you can use as a finished part.
It might be helpful to say, like, at the lower end, they run around $1,500.
Yeah, I mean, you can
Yes.
build your own 3D printer these days. I mean,
And then at the
not
higher
every-
end, you're talking about $40,000-$50,000.
Yeah, you go higher, you can $70,000.
And also about the materials, the range of materials we use in 3D printers, what are the limits of interesting?
Yeah, there's different, there's powder use, some of them are more powder based. Those were like the early printers, and the kind of higher gauge printers, the more precision oriented ones tend to go with powder. In fact, the University of Texas, I think, is coming out with they've been testing a new system where it's not additive. Well, it is additive, but it's not based on creating, depositing. It's not based on depositing. What it's based on is that there's an arm that spreads powder onto a piece of table, let's say, and then a laser projects the micro sections of what you're trying to print every time. So it's fusing instead of depositing. So it's like super accurate because your accuracy is basically laser accuracy.
Okay, then how do you know how you can use this material, for example, on the facade of the building, or it's not enough strong for, I don't know, for the temperature high or low weak or something? How do you know the features of the
Yeah.
materials?
But I would say most plastics printers, and if it's using powder or if it's using kind of a threaded plastic, it's essentially a plastic-based material, and that needs to be tested as such, right? It needs to go through ASTM testing. So in most cases, that using it on the facade of a material, you'd probably need to print it and then go through testing, which was, I think I showed the example for Gary, for instance, that wasn't 3D printed, but the extruded versions, there was a whole level of testing because it was coming up with a new material, essentially. And once you come up with a new material, you have to test it, right? The metal-based mechanism, which is very expensive right now, will alleviate this kind of issue because it's already, you're dealing with metals. I mean, you'll have to test it for other capacities, but in terms of thermal barrier testing, you won't have those kinds of issues. But for plastic-based material, yeah, you have to undergo testing. I mean, there's
You would
labs
still
that
need
can
to-
do that kind of testing for you.
You would still need to test for wind loads and kind of
Yeah, exactly.
shear and tear and, you know.
Yeah.
I assume from what you're saying that the robots will have this kind of heads that instead of having the 3D printer, you just have that and it becomes a 3D
Yes.
printer, it becomes a laser printer.
Yes.
Color, it becomes everything you were talking about combined there.
Yes, and you can have multiple robots working together. So like imagine 3 6-axis robots working together. So like the capacity, the range of cover you have shifts drastically from a 3-axis.
And was there anything like I had that pores instead of carving or cutting
Pores?
pores in material?
Yeah, I mean they're extrude. They extrude. You can vary the pin size to get more solution to come out or less solution to come out. Yeah, absolutely.
And the concrete panel example, it
That's
looked
it.
like it was pouring, in one
Sand.
case it was pouring sand,
Yeah.
which would mold like a.
Yeah, yeah.
So it's not really taking the place of the labor, but doing much more sophisticated things
Exactly.
in difficult areas and locations
Exactly.
where you can't do it.
Yes. I mean, on a very simplistic level, you're taking the place of labor, but I don't think that my personal opinion is that in 2 generations, labor is going to be kind of versed in this technology. You need people to operate this technology. You need people to post-produce. You know, there's a lot of assembly after many of these things come out of, sort of their fabrication realm. So I don't ever think we're going to get rid of the labor, but it could be more efficient.
But some of the solutions you had required extremely skilled labor because they were, I mean, this is like very high-end labor.
Yeah, that's what I mean by, I think in a couple of generations, the labor force is going to be well versed in this technology. If this technology is really on its way to becoming ubiquitous or being used on a building scale, which we're a long way from that, but hopefully the trend is to go in that direction, I think your labor force is going to be, well skilled at doing that. You already have engineers and consultants that are on board with that kind of thing. Leading engineering companies in the world use, BIM modeling. Who would have thought that 8 years ago, 10 years ago? You had to fight to get engineers to use BIM modeling. Now everybody wants to use BIM modeling, and is their own, kind of initiative.
What is the commercial picture right now? I mean, there are companies who can do for you, you can order them something and they come and they make your facade or a house or something.
In terms of this technology? Well, yeah, in the States and in Europe, there are companies like fab houses that have a variety of this kind of fabrication technology and interface with designers all the time. Not necessarily. I would say it's more, those guys work more in the realm of like installation, you know, smaller scale kind of. But yeah, that's essentially what happens. You know, let's say you want to have something 3D printed in metal. There's a company that does that, and you interact with them to have your final output. There's a lot of those kinds of services. The robot fabs, the robot fabrication is just starting. That's not so common right now. But I have experienced, for instance, in the last couple of years, almost every major institution in the United States that has an architecture school has a robotic fab lab. And grad students don't want to go to schools that don't have a robotic fab lab.
And what about cost comparison? Like if that company comes and does your design by that robots, that's one cost. And then you order an ordinary kind of company construction and they come and by manually they do all that stuff.
Typically when you work with those companies, if you need engineering, that's an additional cost. For them to just give you equipment time is one package sort of thing. So a lot of times what happens is, say if you're doing an installation or something, you do the design, you work with your engineer, it's a done deal, it's a package, all you need is for it to be realized. That's a basic kind of service that they provide. If you need them to do engineering costs, those are other options they have, they can offer you, but it's not a must. You don't have to work with them.
But it's, I want newer technology, better, nicer, better architecture, modern, then I need to pay more to apply this technology, evidently, yes?
Well, I guess I'm not sure. So you wouldn't go to them to have to get the design, to get the package of better technology, nicer design. I mean, you have to. They have the machinery.
Design is mine, and
yeah.
It is curvy, Gaudi inspired something.
But you don't know how you're going to make it.
Yeah.
Is that what you're saying?
Mm-hmm.
Yeah, they could consult with you on that, and you have to pay for that. Yeah.
But that would be more compared to the traditional ways, or not?
As opposed to building a traditional stud wall.
No.
Traditional manual labor.
Manual construction.
Ah, I
Of
see
your
what you're
Gaudi
saying.
wall?
They're
still building Gaudi.
Not necessarily.
You know? If they haven't finished building them.
Not
it's gonna-
necessarily. I mean, the only comparison, the only frame of reference I have for that is if the Beekman Tower in New York, which is this very curvaceous facade system, that was one of the high rises that Frank Gehry did. That actually came under budget when that was for a developer, and they did cost appraisals for kind of a stick figure facade system, a regular facade system, you know, and they had varying line items. That actually came under budget than typical like.
They used flying robots, or?
No, they didn't use flying robots. They didn't use flying robots, but they did use like laser cutting, CNC milling, you know, die cutting, the mullions. I mean, there's a lot of this technology that goes into putting facades together that we never acknowledge. If you have a non-straight facade, chances are you CNC milled or die cut the mullions. But we don't see that as a, you know, aesthetic and don't acknowledge it as that. So.
Yeah.
I have a question. Is it possible to utilize these modeling coordinates to visually map projections?
Yeah, the robots.
On the actual coordinates that they use to map projections on the installation.
Map projections on the. I'm not sure. I know
3D mapping?
3D mapping for projecting around.
Yeah. There was, I mean, I think the specifics, maybe you have to tell me exactly what you're imagining so that I can understand the technical requirements for it. But there's a lot of study for instance, there was a seminar at SciArc where the students were studying how to use the robots to engage with each other in terms of projection. So,
Because there's separate software that I've used before for visual mapping, but I was wondering if you can utilize the same coordinates that they use to build it instead of having to lay the coordinates on your own.
I see.
I'm just wondering because this is very.
I would think that I would think that that could be a kind of a high possibility because it depends on the software, I guess. I don't know.
I guess software.
Maybe we
I
can
use-
talk more specifically after, and you can tell me what you did and what software you used, and I can think about it a little bit.
Okay.
I should point out that, Narine was here working with Tumo for a month almost
Yeah.
with the kids. And the kids came up with lots of interesting 3D modeled and printed objects. Pretty sophisticated, complex stuff.
Yeah.
And they did it in 3 weeks. They learned it in 3 weeks. From scratch, right? They didn't know. 5 weeks. From scratch, right?
Pretty much. Yeah.
Pretty much, yeah. So it's really exciting that kids can pick this up and really play with it. I wish we had some photographs of the stuff they came up with. But,
Maybe you can go to Tumo and
yes.
see them.
And thanks for inviting her over. Yes.
Anything else?
Questions?
Other people in this room have 3D printers.
I'm sorry?
There are other people in this room have 3D printers. It's getting more and more popular.
Yeah. We're ready for donations at AUA.
Actually, some are building.
Yeah, when you talk about cost, some of the lowest cost ones are these $600 3D printers
Even that low.
that are designed to be made out of parts you can buy in the hardware store, plus parts that one printer can build to build the next printer, plus some electronics. So
The printer builds the printer?
Yeah, actually.
Escher is coming to life. Yeah.
One quick question.
Yeah.
So at the beginning, you said that when you started architecture, studying architecture, it was really different and you saw the change. So what is now the 4 or 5 years of architectural curriculum? Does it involve all this? How
Yeah,
is
it does.
changing?
It actually heavily involves all this, but not, so I saw a shift in the last few years. If you'd asked me 10 years ago, I would say that the design industry, the architecture industry was really obsessed with tools, with technology, and tools were driving that process. But as those tools have become more available to everybody, I think the industry's realized and kind of matured in the way that they think about these tools and the way they use these tools, that it's not about the tools, it's about the process. And so now it's very, very much about process, very much focused on how can we design not just the object or the end result, but the process. Can we design it? Does that make a difference? Can we expand authorship, in terms of fabrication process as well as design? And so, some of these examples I'm showing may seem really trivial and kind of out there, but it's the kind of proof of concept research that's happening that is going to be really important in our field, in expanding our sort of, I'm talking as an architect now, or a designer even, in expanding our reach in terms of what happens in our built environment. So, I think that's a positive move or a positive realization in terms of the industry and kind of recognizing that, okay, these are just tools. We have to kind of dictate what we do with them.
May I go? The thing is that in practically any human activity, things go in a kind of Foucault-Pandian way. It goes from tools, process, back to tools, then again to process. So it's very natural dynamics.
Yeah. But I hope in some way we sort of, when we circle back, we kind of, at least we move forward, is what I'm trying to say.
I think over time also we'll start finding some form of logic in this impossible for human to build structures, right? So we have to rely on robots. Because it would just cost enormous amount for human beings to try to build it without any kind of mechanical help. Do you see an end to this, like impossible forms, or it's only going to become more and more?
You mean in terms of robotics being used for, like, as labor, or?
I'm just thinking, you know, we're pushing the boundary of form because we have this technology.
Yeah.
But it's a technology experimentation more than, and there's some aesthetics to it, but also there's got to be some kind of rational boundary to it, right? Or am I just being too conservative?
Why does there have to be a boundary to it?
I mean,
In
laws of
academia,
economics.
why
I
does
mean,
there have to be
just
a boundary to
economics. Just basically, you have to be efficient.
Well, okay, I would say in practice, I agree. And that, you know, we have practice and we have academia, right? That's part of our profession. I mean, at least for me, those two things are very important. And in academia, I don't necessarily think you have to be efficient. I think it's okay to be, you know, it's okay to at the expense of being efficient, drive ideas forward. In practice, I understand, because you're dealing with lots of, you know, you're dealing with budgets and you're dealing with real life repercussions of something being there for many, many years. I mean, there, yes, you have to be much more calibrated and efficient and responsible, and all of those very heavy kind of considerations. But I think in academia, I don't necessarily think we have to be efficient. I'm not sure it's a good focus to have.
I meant the profession more than the academic.
I mean, and in the profession, I think it's a trade-off. We should worry about it. I mean, we should be concerned with being efficient, but not necessarily at the cost of not doing anything interesting either. You know, it's a balance, I think. Sometimes over-efficiency, you know, if you're not analyzing it correctly, doesn't necessarily have the benefit that, you know, doing something that would seem to be a little more indulgent would give you. But I agree with you in the sense that it's something that you do have to consider in practice. And I don't know where that boundary is yet. Because I don't think that this technology's made it to practice. It's not made it to, like, the robots haven't made it to building scale. Like, there's thesis work being done at UCLA with building scale robotics, rooms that move, not just doors and windows, but rooms that move, floors that move, that kind of work being done. But that's, like, you know, the one of the few cases of its kind that I've heard of.
Is it the right impression that I just got that actually architecture and design solely are kind of inspiring and driving probably the building new type of robots, building new type of equipment for this direction? I have that impression, but I might be wrong.
No, I think that's the right impression to have, right? I mean, I think that with the robot fabrication, that is the direction that it's going, that architects can actually, I mean, I think in few years, in maybe the earlier part of this decade, it was about material. Architects wanted to create material. So it was very much about those technologies I talked about earlier that would somehow manifest themselves in a material system, like milling something that would be a new panel system, or, you know, there's many examples. And now it's really, yeah, it is more about the kind of designing the process, designing the technology, or at least experimenting with what happens, you know, the what ifs.
But there are already pretty advanced systems in industry that's being used, right? I mean, these are imports from manufacturing,
Yeah,
right?
but only for prototyping, not really manufacturing. My impression is no, I mean
No,
this
they're-
kind of prototyping.
They're used in the difference is that I think in the industry they have very specific use, as opposed to, I think, you know, in the academic realm right now, people are trying to think about it as you can customize end-of-art tools and have varied use.
Any questions?
I have a quick question about your interaction with the TUMO students and over the 5 weeks, because I'm watching this, and although I'm at TUMO, I never had a chance to actually see what you showed them, and I can't help but think how fascinating it must have been for them for 5 weeks to be in this world and then to go into this world. And I'm wondering if you had any conversations, ideas, thoughts that kind of were whirling in that classroom between sort of the application of this
Yeah.
in any small way to what's going on, you know, on our streets in Yerevan, and if there were any light bulbs, or, I mean, just curious, this is a very vague question, but that's how I feel sitting here.
No, it was, that's a good question. I mean, there were, I mean, at first, I think it was more like, really, where does this fit in? But the more we talked about this and the more we got into the technical aspect of them actually working in Rhino and working with the 3D printers, I think the context made sense to them. And just funny anecdote, I had a couple of students who separately came to me like 2 weeks, 3 weeks later, after we'd gone through some of these technologies, and we're putting kind of techniques together. Like, so I want to make a ring, and I want it to be, but I thought that was such a practical application of what they can do with this technology, and I think that was great, because they got it, right? I mean, it's okay, not all of them are going to be architects, not all of them are going to be designers, but the fact that two separate individuals came and, asked about a specific technique with respect to making a piece of jewelry, like, I felt like, it was a productive 5 weeks in that sense.
So what are we going to do with them when we let them loose and they're like
You gotta
30
buy some
and they're
robots.
living here? What are we going to do with
Buy some new jewelry?
What's that?
Buy some new jewelry?
Buy some new jewelry.
Architects?
Thanks.
Any questions?
Okay, if there are no more questions, Narine, thank you very much on behalf of College of Science and Engineering, and thank you all of you for your presence. Thank you.